In this last video, I'd like to go over two more examples with slight differences from our first, most elementary example for finding the volumes of revolution with the disk method. For our first example, we'll be looking at the region in the first quadrant that's between the positive x-axis and the curve y is equal to the sine of x, as x goes from 0 to pi, and what we'll be rotating around is the x-axis. So just like we should do with every single problem that involves volumes of revolution, finding the right solution begins with finding the right picture. So we graph our region in question. Here's our curve, f of x, on the interval from 0 to pi. We'll be placing rectangles between this curve and the positive x-axis, and then we'll be revolving them to form cylinders around the x-axis as indicated right here. The process then is to identify the height of one of your basic cylinders and the radius of one of your basic cylinders, and then to use the formula for the basic volume of a cylinder. So as it was in our previous example, what's defining the height of our cylinders is what was previously defining the base of our rectangles, and that's this tiny difference in x values denoted by dx. What's defining the radius of any one of these cylinders as we're working on the interval from 0 to pi is the distance between the x-axis and the curve, which is just a fancy way of saying the height of the function. In this case, sine of x. In the last example, square root of x. Our formula for the basic volume of a cylinder is pi times the radius squared times the height. And so all we've done here is added the pi, squared the radius, and multiplied by the height. And this expression is a generic formula for the volume of any one of these cylinders that we see on this interval. To obtain our total volume then, we'll integrate over the starting x value we wish to consider up to the stopping x value we wish to consider. And the integrand should be our volume formula from the previous step. The only thing I've done here is taken the pi on the inside of the integral, and because that's a constant, we moved it to the outside of the integral. Now if you're using a computer algebra system, we could stop right here, and once we have this integral, we could type it into something like Mathematica and get an answer. If you're integrating by hand, which sometimes you have to do, I'd like to just use this as an example for review, and to show one more trick that can sometimes be useful. So for the sake of review, I'll be working this integral by hand in order to complete the problem. One thing I'd like you to notice is that at x is equal to pi over 2 right here, we have perfect symmetry in both the area and the volume that we have of this region, meaning that the area beneath this curve to the left of the line x is equal to pi over 2 is precisely equal to the area to the right of the line x is equal to pi over 2. And we could cut this region in half if we wanted to, and simply find the volume of our shape between 0 and x is equal to pi over 2. And then if we wanted, in taking half of that interval, we could double the answer, and what we would be left with would be the same as the integral that we have right here. Again, that's not really a necessary step, but every now and again can be a computationally useful step when we have to do these problems by hand. For this example, that step is particularly useful for the following reason. In order to integrate the sine squared of x, we're going to have to first use a half angle formula from trigonometry to switch the sine squared of x to 1/2 times the quantity 1 minus cosine of 2x. Because I have a 2 sitting outside of this integral, and I'm going to gain a 1/2 from the introduction of this half angle formula, the 2 that I had from the doubling of my symmetry, and the 1/2 that I have from implementing this half angle formula to go from sine squared of x to 1/2 this quantity, perfectly cancel each other out. And that simplifies the algebra that we're going to need to work by hand for this particular problem. Once we've done that and applied our half angle formula, each of the things that we have as the integrand at this step are easily integrable, The 1 we integrate to get an x, and the negative cosine of 2x we integrate to get a negative 1/2 sine of 2x. And all that's left of this problem is to evaluate this expression from x going to 0 to pi over 2. When we plug in pi over 2 for x, that's one thing that we'll have right here, but the sine of 2 times pi over 2 becomes a sine of pi, which is a 0 and wipes out this second term. Both of these expressions, the x and the 1/2 sine of 2x, evaluate to 0 when x is equal to 0, so the only term that is non-zero in this evaluation process is the x term when x is equal to pi over 2. So altogether, that makes our answer for this integral pi squared over 2, and that's the volume that we have visualized right here. Now the last example that I'd like to work is an example of using the disk method when we're rotating around a line that is not the x-axis. And the reason that I'd like to do this is because when you have this strategy that we've been doing all along in this video, I find it a lot easier to rotate around a different axis by using the right picture and following the steps we've been doing all along. So I'd like to do this example to show you just how little we have to change to rotate around a line that isn't the x-axis. For this problem, we'll be considering the area in the first quadrant between the line y is equal to 4 and the curve y is equal to the quantity of x minus 2 squared. We'll be working on the interval from 0 to 4, and we'll be rotating around the line y is equal to 4. Just as we did with the last example, and just like we should do with all volumes of revolution problems, we begin with a picture. The right picture can really take us a long way towards finding the answer to these problems. So right here is the line y is equal to 4 in black. This blue line right here is our curve, the quantity x minus 2 squared. And what we'll be rotating around the line y is equal to 4 is the area that's trapped between those two lines. So that's where we've drawn our gray rectangles this time around. Notice from this picture that we can visualize that this whole volume could be determined by finding the volume of small cylinders and adding up the volumes of each of those cylinders. So the approach should be absolutely the same as we've been doing in previous problems. We should look at the picture of our basic cylinders. We should identify the height and the radius of those cylinders, and we should then piece everything together. Just as it was last time, the height of each of our individual cylinders is going to correspond to what was the base of each of these rectangles, which is this small change in x value denoted by dx. So absolutely nothing has changed in this part of the setup of the problem. What has changed, and is what is worth spending our time talking about, is the radius of each of these cylinders. In our previous example, the radius was found by looking at the height of one of these rectangles, and the height was the distance between the positive x-axis and the curve. That was what was defining the height of our rectangles. In this example, we don't have our rectangles underneath the curve. Our rectangles are above the curve. But what is still true is that the distance from the positive x-axis up to the curve is given by our function. What we're interested in is the difference between the line y is equal to 4 and that distance. Or in other words, the total distance between the positive x-axis and the line y is equal to 4 is 4 units all the time. And always the distance between the positive x-axis and the curve is given by the height of the function, in this case, the quantity x minus 2 squared. So the gray distance that we are looking for should be the difference between those two distances. The total distance of 4 units up to the axis, and the distance from the x-axis up to the curve, which is given by our function here. So our radius, this gray area, is given by total distance minus this distance. After we make that change, absolutely nothing else needs to change about the way we work through these problems. It is still the case that the volume of one of these individual cylinders is given by pi times the radius squared times the height. And if you do the algebra to expand out this square and then consider 4 minus that quantity, what this will be algebraically equal to is negative x squared plus 4x. And as we have done in all of the other examples, the total volume will be found by summing each of the individual volumes. If we take the pi, as we did with the last example, which is a constant, and move it to the front of the integral, if we expand out the quantity negative x squared plus 4x squared, we'll end up with x to the fourth minus 8x cubed plus 16x squared. And when it's written in this way, it's easy enough to integrate term by term. And a little bit of messy algebra will tell us that the final volume of this whole region of revolution is 512 pi divided by 15.